conectando. Y aquí lo tienes. ¿Quieres que se vea más grande?
Como quieras, me da igual.
Esperemos que no se cambie de allí. No, allí no cambia, ¿no? Entonces, lo que pasa es que para que... Vale, ahora creo que ya está todo.
Tengo el mando a distancia.
Tienes el mando a distancia. Voy a ¿Te explicas?
Sí, así a paso.
Voy a apagar esto.
¿Tenemos un minutillo más? Let's start. Good afternoon, everyone. Welcome to our IPARCOS-seminar. Today I'm pleased to introduce Professor Alexander Knebe. Alexander obtained his PhD from the Potsdam University in 1999. Then he had the postdoctoral position at Oxford University, Swinburne University, and Leibniz Institute for Astrophysics in Boston, where he was awarded the prestigious Neighbour Fellowship. He then moved to Spain in 2009 as a Ramón y Cajal Fellow at the Universidad Autónoma de Madrid. He became associate professor in 2014 and a full professor in 2020. Currently, he's the director of the Department of Theoretical Physics at Autónoma University. Alexander is a distinguished cosmologist and astrophysicist focused on near-field cosmology, galaxy formation, and high-performance computing, with over 190 peer-reviewed publications and more than 9,000 citations. He has supervised numerous PhD and master students. His extensive experience also includes teaching, committee work, and reviewing for scientific journal and funding agencies. Today, Alexander will present on the topic use constrained local universe simulation. So thank you very much, Alexander. The floor is yours.
All right, thanks a lot for this very nice introduction. Are you sure you're talking about me? I'm flattered. Okay, so I hope I'm still a normal person besides of all of that. Okay, when I was invited to give a talk here, basically I didn't know exactly. I asked you, so what topic should I talk about? Because I am mainly involved in two large collaborations. The one is focused on galaxy clusters, theoretically modeled, and the other one is exactly what I like to talk about today, that is constrained local universe simulations. I picked this one because with the galaxy clusters, there are people here in the audience. Patricia Armando is not in the audience. No, he's there. Beatrice, with whom we are working together, so I thought it's boring to tell you about galaxy clusters. You might know about all of that. Maybe I'd rather tell you about something that you might not have heard about yet. Okay, so the goal of this talk is to introduce you to the Constrained Local Universe Simulations collaboration. And there is also a website related to that. It's an international collaboration with, I don't know how many, close to 100 collaborators. And yeah, it was founded in, I can't even remember, early 2000s it was founded. Right, so what is the deal with this? So obviously it's about cosmological simulations, but then why do we need constrained simulations? So that's the first part of my talk that I would like to start with, to show you the difference between normal simulations You have heard of the Alaska simulations, maybe, the Eagle simulations. Right, those are also cosmological simulations, but they are not constrained. So what does it mean with constraint? Constraint really means that we want to model, theoretically, the actual local universe as it is observed. Because these other simulations, all the other simulations are basically random simulations. They model a universe that has the same statistical properties, hopefully, as our universe. But it doesn't have the Milky Way, it doesn't have the Andromeda galaxy, it doesn't have the Virgo cluster. So the aim of this collaboration was to, why don't we try, by whatever means, to model the real universe. You might ask, why do we want to do that? Actually, I don't have that in my introduction. The motivation for clues. I should have put more slides about the motivation. So, why do you care about modeling the actual Milky Way? The Milky Way is just a disk galaxy. About this galaxy, you have plenty of those in other simulations. Because we observed a lot of peculiarities in our local universe. To start with, who has heard of the planes of satellites? Right, so this is, if you actually go to one of the most recent reviews about the outstanding problems in lambda CDM, I think this is one of the left and most outstanding problems to explain why the satellite galaxies of the Milky Way and also the satellite galaxies of the Andromeda galaxy, they are living on a plane. They are co-rotating on a plane. Why aren't they randomly distributed like galaxies in a galaxy cluster? And we observe that, but it's very difficult for random simulations to reproduce that. So that's part of the motivation for doing constrained simulations. So what we really want to do is, we want to do a simulation of cosmological structure formation, but end up with the local observed universe as best as we can. And that was the objective of this collaboration. How do you do that? Actually, I'm not going to go into the details how you do that, that's rather technical. I show you some of the constraints that we are using, so where does this word constraint actually come from? But I would rather like to focus on some of the science that comes out of it. Okay, so this is the structure of my talk. You haven't seen that. I prepared 318 slides, so I hope you brought a lot of time with you. No, look, I already explained Patricia. This is a talk in progress. So actually, I started this talk maybe 15 years ago, 20 years ago, with the introduction, and then whenever I published a paper, I added the results to it. So at the moment, there is a whole list of results that you actually can pick from. So I will show you a list, and you can pick, oh, we like to hear about that, oh, we like to hear about that. However, there is one thing on this list that I definitely want to show you. Something that who has heard of the Council of Giants? Gotcha. And I'm going to introduce you to the Council of Giants. Okay, so actually, let me also see that, so who is familiar with cosmological simulations? Who knows exactly what a cosmological simulation is? Okay, maybe we even skip that part then and rather go to the interesting science questions. But nevertheless, allow me at least to say a little bit of the general blah 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 as an introduction. So, what we are doing here with local universe studies is basically, the term was coined by Ken Freeman in 2001, I guess, near field cosmology. We have the best possible observations in our local universe, but they are certainly also affected by cosmology. And cosmology leaves an imprint in our local universe. So that's where the term near-field cosmology comes from, that you will see all over the place here. But let's first start with the very basics. So this is a sketch of the evolution of the universe, and it encaptures structure formation within a cosmological framework. So where is the cosmological framework in this plot, and where is structure formation? The envelope here, that's the cosmological framework. That's the extension factor, the one that you find in the Friedmann equation. You can solve that analytically. I don't care about that. Give me a cosmological model. Sure, this envelope will change, and it will certainly affect the structure formation in here, but that's actually taken care of analytically. I can get an analytical solution for the frequent equation. But what I cannot get an analytical solution for is the nonlinear structure formation that I find here. So it starts all with the anisotropies in the CME that basically provide the initial conditions to these simulations. And then I plug those initial conditions within this analytically handled framework into a computer, and then I wait for a few months on Mare Nostrum, and then I get the results that hopefully resemble what I observe here. But what do I observe here? Yeah, okay, the framework is dictated by my favorite model. So what do I observe? I have two possibilities. I can go for large surveys, like what everyone is raving about at the moment, JWST. Well, actually, JWST goes very far afield. The first galaxies in the universe that we have already found beyond redshift 10, or Euclid, for instance, that focuses on redshift 1. They want these surveys, they want the map of the whole universe. What does this map serve for? In terms of cosmology, because of cosmological distances and the structure evolution involved in that, we are able to fine-tune cosmological parameters. You might say, why do we want to play this game? Because with Planck and WMAP, we already know the parameters, but this is orthogonal. And this actually probes the accelerated expansion of the universe. Here, we don't have a good handle on the accelerated expansion because things are still linear. And acceleration, the lambda term has not taken over yet. But at late times, here where we have the large surveys, like Euclid, for instance, we are actually probing the time where the acceleration takes over. And that allows us to distinguish models with or without dark energy, evolving dark energy, or whatever. Okay, so they have real cosmological aims at understanding, again, going back to this feedback loop here, the framework. It works well on large scales, but one of the problems is if we take, now one is, I forgot, so what are you seeing here? You see surveys and you see simulations, but maybe it's the other way around. Yes, these are the surveys. Who cares? They look great from a distance. So everything seems to be working with our favorite lambda CDM model. It seems to be working. If we now go into the details, because every dot here is a galaxy, but if we now go into the details, like let's study the galaxies in fine detail, let's look at the mass profiles of these galaxies, let's look at the distribution of satellite galaxies about these galaxies. We are seeing differences between simulations and observations. And in particular, we see the differences in the local universe because we have the best possible observations nearby. The Andromeda galaxy is one of the best studied galaxies. I mean, you resolve the stars and everything in there. So, can we somehow make a connection? And the problem is, if you now look for Milky Way lookalikes in these types of random simulations, yes, you will find them, but they don't agree with what we observe. Not at a 100% level. They agree from a distance, but not at a 100% level. So again, that's then the motivation for actually going to constrained simulations. There is another thing. Actually, that was a problem mentioned way earlier, the missing satellite problem. It all started with that if you count the number of dwarf galaxies of the Milky Way / Andromeda, like 15 years ago, you had like 12 for Milky Way, 13, 15 for Andromeda. But these simulations, these types of numerical simulations tell you there should be tens of thousands. So that was the first problem, missing satellites. It might be under control. But the planes is still something that's not really under control. Okay, so this is a picture from one of my first PhD students back then. The plane of satellite galaxies drawn as an artist impression. Okay, this is not a plane of satellites, this is just the orbit of one particular satellite in the Milky Way, and you can see that there is a lot happening. That there is a lot of information that we actually do observe. We do observe these stellar streams in the Milky Way and in the Andromeda. And if we are lucky, sometimes even for galaxies that are farther away. But again, the best observations are here. You can do now chemical tagging of these stars and try to figure out what is the progenitor of it. All this business you can do in random simulations, or you can do it in constrained simulations. So how do we match that? Yeah, that's the question. Actually, I think if you or let me quickly skip through that, because I actually said all of that already. So you start your simulation with putting initial conditions into a computer. Where do they come from? They come from not exactly from the observations, but from theoretically modeling the anisotropies that you see in the CMB. You can analytically model that, and then you create a density field that has exactly the same type of perturbation characteristics. Plug it into computer, take your favorite simulation codes, there are various of that, those gadgets, you might have heard the name of that, are Repo, there are Ramses, lots of these codes, they don't disagree, they don't disagree with each other, would be a version. They do not all agree with each other in the modeling, but that's another talk. Then you get a meta field a meta field, and then you need to do something like software telescopes to actually go into this universe that is just a meta field, and you need to pick out and say, this is a galaxy, this is a galaxy. Nah, this looks like a galaxy, no, but it's not. So this type of thing you need to do then. None of that is trivial, but I'm not going into the details. But maybe a few words on the constraints. So how do we actually put the constraints in there? We are not the only group in the world that's doing that. I think there is at least one more, if not two more groups, trying to do the same thing, to model exactly the observed universe. But we are the only ones to do it. I need to be careful, this is recorded. We are doing it differently than all the other groups. Because we are using velocities. The others are using density maps. So they observe the local universe, they create a mass field, and then they put constraints in here on the mass field. We are using velocities, because velocities directly probe the potential without the need for a gauge. So that's why we are actually using velocity fields. And what you see here is basically a visualization of the actual field that we are using. The observations were done in collaboration with Fred Tully and Hélène Courtois, and the survey that they have done is called Cosmic Flows. They measured all the radial velocities of all the galaxies in the local universe. It's a great undertaking. It took several years in Hawaii. We got a priority access to the data, and we use those velocities to constrain the velocities and the density map, in the end, the phases of our initial conditions. Don't ask me the details, I'm not involved in that technical aspect of it. Basically, my field of interest comes with running simulations and in particular analyzing the outputs. And I spent a lot of time writing papers with the outputs. Okay, so this is one of the old simulations. This is not the newest simulations, but I should have put a mass map of the mass map of the real universe is here and here. I don't know, we're not good at public relations. Other groups are better at public relations. So we should have done a similar plot with the real observed universe to prove to you that this is okay. But if you believe me, yes, we have Coma, we have Virgo, Perseus, Pisces, we have the Great Attractor, and in here, somewhere in there, we really have the Andromeda Galaxy, Milky Way, and M33. We have it in here. Actually, do I have that paper? Yes, I actually have this paper on my list. Andromeda and Milky Way are flying, not obviously, but this is also observed, towards the Virgo cluster, but in two distinct tiny filaments. So, this is something that we get also in our simulations. It's not the latest one. The latest one is actually called Hestia. So what's the difference between this one and the very latest one? We moved to a new more sophisticated simulation code. Actually, not really. Yeah, it is more sophisticated. We moved from Gadget, which already is a very, very well-tuned and highly sophisticated code, to REPO, which basically is the successor of Gadget. And we moved to a new subgrid physics model. Okay, what is subgrid physics? In those simulations, you are not able to ab initio model the formation of stars. We are a far way from being able to do that. So, because we use particles to sample the matter distribution, and we also use particles to sample stellar material in the universe. But one of our star particles weighs 10 to the 4, 10 to the 5 solar masses. This is not a star. This is a collection of stars. So you see, if we form a star, it's a star particle in simulation. It's not really a star, it's a collection of stars. But how do you form the star? And what collection of stars is it? What IMF does it have? What mass function? What properties does it have? And that's the so-called subgrid modeling. We need to make assumptions for that. And for this particular suite of constraint simulations, we use the so-called Auriga model, which is the one that was used by the Illustris team for their Illustris TNG simulations. So that's the kind of model. So we went from, look, all of this started in the early 2000s, where we used whatever was fancy back then. But at some point we said, we now need to move to something more modern. So we collaborated with the Illustris team and ran our Clue simulations with the latest version of their code. And that's the suite of simulations that you find at this website that you cannot read. It's called testbed.aip.de. Or just ask me if you are interested in these simulations. Yeah, I just said that. We published, since the simulations are finished, they finished a few years ago only, but we already published quite a number of papers coming out of those simulations. And, right, okay, so I gave you the PowerPoint, but it's still a little bit screwed. If I look at that on my computer, it looks better. So this is basically the list of topics that you could pick from. Let me say a few words about this. As I said, while I was going along, I started adding papers to this talk. So these are the oldest results, and these are the newest results. And I told you that I would actually like to present one result to you that's not yet not based on the CRUISE/HESTIA simulations, but I also wrote an observational paper. That's the only observational paper that I wrote in my whole career. How many publications were there? 100 something? They are all simulation papers. No, I have one observer. And I'd like to show that one to you. And that's the last one here. The Council of Giants. Okay, so let me jump to that paper. I hope it works because these are Control-click to follow the link. Yes, it worked. Okay, it was quite an effort to get all these arrows working and jump to the right slide, but it's working, I hope. I hope that the next slide will be the Council of Giants. It's here?
Yeah, move the mouse to that screen.
How do I do? Where is it?
To the left of your main screen.
To the left?
Yeah.
There is, okay, now it's left? Now I need to click. Okay. Okay. No, it didn't work on what I had. I don't want to search this now, but okay. There you go. Now it worked. Okay, so the Council of Giants. So what is the Council of Giants? That's a project that took far too long in my life. I think it's the writing the council. This is not my Council of Giants paper. This is how it all started. But it basically started nearly in 2014. I think it was the CLUES meeting. We have annual collaboration meetings. And I think in 2015, someone, I think it was Andrei Kravtsov, mentioned that there was this Council of Giants paper by McCall, and whether we as the CLUES team have looked in our simulations if there is a Council of Giants. And then I started it, and the paper was published this year. Right, it was like a tedious process. I should also say that I burned, I don't know how many trabajo fin de grado and master students on it. I mean, I think there are 3 or 4 trabajo fin de grado / master theses written about the Council of Giants. They all got high marks. I hope. Okay, anyway, I'm getting carried away. Let me start with this particular paper. So what did McCall do? McCall basically plowed through the literature. How to start? There is actually, but he didn't use it, one single catalog of the local universe. There is a catalog that's done by Dimitri in Russia, but he didn't use that catalog. McCall plowed through the literature, trying to find all the properties of all the galaxies in the local universe. And he created a table that is like 4 pages long of the most prominent galaxies in the local volume. So this is within, I don't know, 10, 12 megaparsec radius about the Milky Way. Fair enough, great effort. But then, okay, what can you do with this data? You can visualize it. So he looked at it, and that's what he found. He found that here, Milky Way and Andromeda, here in the center, but then, okay, forget about the circle, because he didn't draw it with the circle to start with. He just looked at the most massive galaxies. What do? You look at the most massive one, at the least massive ones, you look at the blue ones, you look at the red ones. This is curiosity. You just look at the data. And when he looked at the most massive ones, he found that they basically form a circle in a plane. So this is not a sphere, this is a flat thing. And these are all massive galaxies, and they are sort of surrounding the local group, the Milky Way and Andromeda. So that's why he called it a council, like with the judges sitting there and observing what they are doing in the Milky Way. The structure is not going away. So there is this ring. It's not like an accumulation of objects in one corner. It's equally distributed according to the angle and inside the plane. So 14 galaxies in this magnitude range at equidistance and equi-angle distribution. Right, what is this structure? Is this a coherent structure? Is this a non-coherent structure? Is this a temporary structure? What is it? I mean, he didn't speculate. He just said it's out there. And then, as I said, that triggered the interest, like, do we find this in CLUES? Just like, let's have a look. But the thing is, how do you search for this? So, again, I spare you the details. I told you it took 10 years to do this. And we haven't looked in the simulations yet. So what have we done? We basically said, look, this compilation of data is very old, going through the literature. There must be something more modern. There are more modern surveys. There must be revised collections of the local universe. Yes. Okay, so 2 questions. Can we find it in simulations? And actually not only in CLUES simulations, it's also in random simulations. But then the question, while doing that, actually one of my colleagues said, why don't you just first confirm whether what you are looking for really exists in the universe? And it's not just a random thing in this table. So we started in the end then with observations. So I had to learn how to access observational data. And there is this local volume galaxy catalog. It's open source, Dmitry Makarov from Russia. He compiled this data. You can download it. I do not recommend you download it. I thought that I am old school because I use C as my programming language. This data catalog was created with Fortran in mind, like having bits as indicators of certain things. So you download the data as an ASCII file, and it contains a weird combination of numbers, symbols, letters, and with a README file telling you, yeah, you need to bit shift this to there, and fair enough, Dimitri is a close collaborator. I just asked him, do it for me. Please send me something that I can read with Python. I am modern. Okay, yeah, so we have these thousands of galaxies, unbiased. Let's look for a ring. But then the thing is, yeah, unbiased. We want to look for a ring in an unbiased way. We don't want to check whether those galaxies mentioned here by McCall, do they really form a ring or not? No, this is not how you do science. Huh? We want to go into this data and we want to search for something. So here are all the galaxies within 10 megaparsecs about the Milky Way. And now we want to find the birth of prey in there. So mark all the fields where you can find the ring in an automated way. So after a few after a few bachelor students, there was one who said, machine learning, buzzword machine learning. Everyone is using machine learning these days because I started to write my own code, like looking at kernel density estimations about the Milky Way, but that already is biased because I assume that the center of the ring should be at the Milky Way. Another trabajo from Negrado sign off. So that student said, machine learning. Let me go and find something. Yes, and he found something. Okay, this is the paper that we published this year. So he found a method called Random sample consensus. We called it RANSAC. And this method is a mathematical method using machine learning where you define an analytical formula for a structure, and then it goes into a point set, a 3D point set, and tries to find it. Okay? Very simple. You can define a cow, you can define a house. We used a circle. So we defined a circle, but with freedom in the position and with freedom in the radius. Okay, to cut a long story short, this is how it looks. There are some technical parameters. We had to assess the quality of the rings found because we want something that is really, really high quality ring, not like, yeah, that could be a ring. So we added something on top of that. We wanted an equidistribution of the points because the method tells you, yeah, this is a ring. Because this pile, and this pile, it forms a ring. But that's not what we want. We want an equidistribution, blah, blah, blah. So we added things on top of that. And then in the end, we called it HINORA. HINORA, high noise RANSAC. Something like that. I don't actually know why he called it high noise. No one stumbled across that. It should be called low noise. And not high noise. Anyway, the paper is published, the name of the method is fixed, end of story. Okay, so we go to the data now. And what do we find? Okay. Now let me skip that, because maybe you want also to hear something else in my talk. And basically just focus on the lower line here. So we did several stellar mass cuts. Okay, we are only interested in the massive one, so forget about that row up there. So this is for high stellar masses, so massive galaxies, and we confirm that there is a council of giants. The blue circle is the McCall council. The red circle is the one returned by our automated method for massive galaxies. Massive, larger than 10 to the 9, 10 to the 10. 10 to the 10.5 in stellar mass. If you believe that K-band magnitude and stellar mass are more or less linearly correlated. Okay, so we find it. Maffei 1 was actually included in McCall's council. There was a lot of... the LBG catalog has an updated distance to Maffei. So the old literature that McCall used gives a lower distance to the Milky Way. So that's why Maffei is not included in our ring, but in McCall's ring. But in the end, who cares? we do confirm there is such a structure. Okay, and it's also in a plane, it's a ring, it's equally distributed. Forget about that upper ring there. This is it dropped out, and I would call that actually high noise. Okay, we made several tests to confirm that this is really a stable structure. I'll skip those plots, believe me, it is. So, yeah, that's the end of the story of this one. We have confirmed the Council of Giants. It is really there in an updated galaxy catalog using a totally unbiased method to find such a structure. Let me mention in passing something funny. No, actually, I don't mention it in passing. No, I actually do mention it in passing. Because you could do another type of search for the structure, which is calculating the two-point correlation function. And then this structure should stick out as a peak. Sure, it does stick out as a peak at exactly the radius of the ring. And you know, this is, I mean, the student who did all of that he started as a bachelor student, he finished this as the master thesis, and he's now a PhD student. He's an awesome student. Anyway, he's very independent, very dedicated, very interested in the subject. And who knows the Tully-Fisher paper? Tully and Fisher. You mean this paper here? This is another paper by Tully and Fisher, where they calculated the two-point correlation function of galaxies in the local universe in 1774. So he found that paper saying, let me see if there is another way to confirm this. He did this calculation himself. Like, this was in 1 week. He came back after 1 week saying, look, I tried this, and I found this paper which agrees. So they already found it. Tully and Fisher already found it in 74, this peak in the two-point correlation function. So, to cut a long story short, yes, there is such a structure. Now the big question is here, what does that mean? What does this mean? Can we find the structure in random simulations and or in constrained local universe simulations? And this is one of the projects that now this student, master, he passed on to be a PhD, and he's working on that at the moment. If I had a little bit more, I had enough time. No, if I had a little bit more time, I could have put some plots up there, because last week he showed me the first results. You want to know them or not? Okay. So, no, what do you guess? Do you find, how do you do this exercise? You first go to a random simulation and you need to find regions that are similar to the local volume. Okay, in random simulations. So, yes, we did that. So we have our, X random regions. No, regions from random simulations that have a Milky Way and an Andromeda lookalike in it. Then we go to the clue simulation and do the same thing. And then, using that data, like this 10 megaparsec region in these two types of simulations, we let loose Hinora, unbiased way to find rings. Okay, question. Random simulations. Do you think we find a Council of Giants? Who thinks we find a Council of Giants? You better do it yourself then, we couldn't. I passed on the data to you and you tell me where they are. Okay, now we go to constraint simulations that are designed to match the observed local universe. Who thinks we find the Council of Giants in that? Nothing. We cannot find it in neither simulation. I don't know why. But it looks like, maybe I have this, do I have this slide here? This is a nice paper that's also based on the Cosmic Flows survey. Also, I didn't know about that paper, my student found it and showed it to me, and he put on there the Council of Giants, and he said, look, I bet this is just a chance structure because you have a filament flow here, you have a filament flow here, you have something flowing here. If you just happen to have a galaxy here, 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 and here, you have a council. And in 2 years, you won't see the council anymore. So it's just a transitionary structure. This is something we could have done if we only had velocities for the observed galaxies, but they were not really all available, or maybe they were, but we were too stupid to understand what they mean or where to get them from. But at least now but in the simulations we don't find the concept. So I think this is the interpretation. So what is the punchline here? Not really interesting, that thing, right? We don't find it in simulations. We cannot theoretically reproduce it. I think the punchline here is we really need velocities for the observations to check whether these are just randomly flowing in opposite directions or converging towards the Virgo cluster. I don't know. I think it is not. I mean, my hope always was that this will be hotter than the plane of satellites. But it's not. It's not. Okay, c'est la vie. We have to live with that. Okay. I don't know how much time I have. I used a lot of time already for just one subject.
20 minutes left.
20? Okay, I mean, up to you. I can present all of that to you. But now it's up to you. Pick something.
Too big to fail.
Sorry?
Too big to fail.
All right. Okay, so let's jump there. Oh man, I haven't talked about that, I think, in 10 years. I hope I still remember. Okay. Okay, so I know why you picked too big to fail. Who knows what this too big to fail actually means and where it comes from? There was a paper by Michael Boyle and Coltrane back in a long time ago, 10, 15 years ago, where he pointed to another problem of the lambda CDM model when you go to the local universe. So, what is the problem? What did he do? He checked, okay, I need the blackboard, because you go to rotation curve of galaxies. Okay, so you plot them, and they are characterized, okay, so everyone keeps saying they are flat, they are not flat. If you go further out, they start to decline at some point, meaning they do have a point, a distance from the center, where you will find the maximum. Sure, this position, there is flatness in it, so you might as well assign that to be R max. It's not unique, but if you are a theoretician, you can find the one point, right? If you're an observer, you might have trouble. But if you do this analytically, you definitely find this pair, R max and V max. And this pair specifies the density profile of the underlying dark matter halo. You just need these two numbers. Because if you shift R max, you change the concentration. If you shift V max, you change the mass of the object. So they are a proxy for mass and concentration in the end of the object. So what Michael Boyle and Coltrane did was, he just tried to get from observations for all satellites of the Milky Way, R max and V max, by whatever sophisticated method. What I'm showing here is basically what I just have drawn there. You can now assume a profile, a mass profile. You can make it NFW, you can make it INASCO, who cares? Every profile will give you a unique pair of Vmax and Rmax for a given mass and concentration. Okay, so, yeah, but there is, as I said, there is in this, okay, I'll skip that. This is the important part. So this is the observations. Okay, so he collected that, and for each object there is a little bit of degeneracy in it. Okay, this is what I tried to explain here, that there is degeneracy in it, and this degeneracy leads to the fact that each object basically occupies a band in this particular space. Okay? Because what you do is, observationally, you measure half the mass, half the radius, the half mass radius. You try to find that, and then you know it's half the mass. And from that, you draw the NFW profile that goes through this one particular observed point. But as I said, you have freedom in the concentration a little bit that gives you different types of curve, and they give rise to these bands now. So for Draco, you observe the half mass radius and the half mass, and then you play with all reasonable NFW profiles that go to this one observed point. And that tells you the region in this Rmax, Vmax space occupied by Draco, Sculpture, Leo, Fornex, and so on. Okay, fair enough. Now you might ask, why did you do this? You can do the same business in simulations. And if you do that in simulations, you basically find this. And there is a mismatch, especially for, so this is the band, should have mentioned that. This is the observed range in Rmax, Vmax parameter space. This is the, and you can do whatever you want to your NFW profile, you will not leave this space. You're unable to leave the space observationally. You're bound to this. So all your simulations must lie within this space if you have the correct objects. And now, this is this band here. This is the observed band. And now he plotted for every galaxy in whatever simulation. I can't remember which simulation he used for that. It must have been something that resembles the Aquarius. Maybe he used Aquarius. Yeah, exactly. He used the Aquarius simulation for that. And in the simulation, each satellite is just one point in Rmax, Vmax. Because you don't have degeneracy in there anymore. You know exactly the profile, you know exactly the point. So you plot that for all the satellites of Aquarius, and what you find is that the massive ones don't agree with the observations. Too big, they are supposed to be too big to fail, but the massive ones are the ones that fail to match the observations. And that's something like, how can that be? They are the best resolved ones. They should follow the best studied properties. How can the big ones fail? If the small ones fail, who cares? You can always write a new proposal saying, we need better resolution, give me more money. But not for the big ones. So that's the too big to fail problem. Okay, that's the introduction to what have we done. This is not in clues. So again, you might say, haha, these are random simulations, everything is random, so you are unlucky. But in clues, it should match. Okay, what have we done? We looked A in clues, and B also played a little bit with the, we used a different subgrid model. Yes, I said all of that already. Okay, what are possible, okay, I start like that. What are possible solutions to this mismatch? One of the assumptions that we made is NFW profile. I told you, pick another profile, pick an INASCO profile, but these observational bands are based on NFW. So the first question is, what happens if you use an INASCO profile or a Burkhardt profile or who cares what, a Hörnquist profile? Maybe those bands then, boom, all of a sudden expand. One possible solution. Maybe the variance. The variance do something to the concentrations. Yes, I mean, why could that be a solution? Because we are talking about the most massive ones. And they have the most mass in variance. So the variance, if they do something, they might have more effect in the massive ones than in the low mass ones. So maybe there is something with the variance. Another thing is this, okay, this, actually I forgot, so the exact relation. The mass of the Milky Way has an influence on this. But don't ask me exactly. I forgot. I forgot exactly how this affects it. Whether you make the Milky Way a little bit more massive or a little bit lower in mass, how that affects the satellites. Or maybe lambda CDM is wrong. Okay, and you see here, maybe some of you know Ariana Vithinzio back then. This is her PhD thesis with me, basically. This part of the study. So we looked at part of it. Or one dark matter. Yeah, but we didn't look into that. So this is one thing. Okay, I skipped over that. Apologies for that. I told you, I think it's 10 years that I last talked about this. So things are coming back to my mind while I present it to you. These results are based on dark matter only simulations. There are no baryons, which is why I put this emphasis here on baryons might have an effect, because these results are taken from dark matter only simulations. So what happens if you put baryons in there? And this had not been done by Woller and Kolkin. We were actually the first to do that. Okay, so what do you see here? Look, students, this is something, always put a legend to your plots. Because I don't forget what the triangle, what these diamonds and the crosses are. There is a legend. Okay, there is a legend. Yeah. So actually, so we have two sets of constraint simulations. One, also only with dark matter, so agreeing with Euler and Kolkin and the Aquarius, and the same simulation run with gas cooling, star formation, feedback, and all of that. And basically what you see in this plot, and look, and in both simulations you can always match this satellite is this satellite. Here it is only dark matter, here it is with baryons. So this is what these connecting lines are showing. They show you this is the position in the Rmax Vmax plane of that satellite in the dark matter one, and it's here in the full physics one. So full physics is actually not explaining it to you. On the contrary. On the contrary, it's making things even worse. This is the thing where the host halo mass comes into play. This is for yet another simulation where we used a different cosmology, and we ended up with a different mass for the Milky Way. And we have observed now that the change is different. This is WMAP3 cosmology, this is WMAP5 cosmology. So I think in the end this is a more reasonable cosmology. So for WMAP3, in the dark matter only run, but who cares about dark matter only? The universe contains stars. But the dark matter one doesn't have the problem at all. If you go to WMAP5, we actually reproduce Euler and Kolkin's problem in dark matter only, but we still observe that full physics, star formation, and all of that included, does not really help. We also played with the profile. Ariana also played with the profile, and Einasto actually made things better. I remember a plot, no, I don't have it on here, a plot where the Einasto profiles are basically extending more like that. Yeah, so that was the work back then regarding the too big to fail problem. I have to admit, the case was closed with me. For me, the case was closed with that. I couldn't find the solution, and I just moved on to something else. Marie-Angelis, you brought this up. What is the status? What is the status of the too big to fail at the moment?
It's not yet solved, so that's the reason why I asked you. Because
it's still not solved.
No.
I mean, Mark Lovell, for instance, investigated warm dark matter. James Bullock also did a lot in that direction. But I don't know. My feeling. This is why I left it. My feeling was that it depends on too many parameters. So I just lost interest in it. I didn't want to tune this parameter or that parameter, trying to solve it. I thought, let other people do it and the problem will go away. But if you tell me now the problem has not gone away yet, it might actually be interesting to return to it.
Yeah, I think it's an interesting problem because it's a mass scale which we're supposed to know better, but we have problems at that mass. So for me, this is quite confusing.
I fully agree, but as I said, when I started to play with it, there was the influence of the mass of the Milky Way, there was the cosmology influence, and INASTO versus NFW, and what exactly is your subgrid model, and too many knobs to turn, for my personal taste.
Yeah.
But if it is still an open problem, then
Maybe we should recall the problem and try to analyze it.
a good starting point would be to find a master student who has an interest in it. Go through the literature and then go to the Hestia simulations and look there. Right, yeah, okay. I don't know if you want to hear something else or if we just stop here.
You have to come with Dave.
Oh, yeah.
How realistic is at the small scale these cross-play simulations? I mean, are you reproducing, for example, the info of the
Natural
clouds?
No, look, okay. I don't think I can skip back quickly. Maybe if I do it manually. I go. I shouldn't have done it manually. Okay, thanks for your attention. No, okay, I wanted to bring up the plot of the cosmic flows visualization that basically shows you the large-scale flows of the galaxies. And that's where we constrain the simulations. On scales larger than 10 megaparsecs, basically. So everything that is below 7-8 megaparsecs is still random. So what we do basically is we constrain the large scales, make the small scales random, run a low resolution simulation, hoping to find the Milky Way and the Andromeda. If we find it, then we start to bump up the resolution. But it's more refined than that because there were several PhD students working on making this all automated. The most recent one, using machine learning, obviously, to get the initial conditions correct. But I can tell you that in all the constraint simulations that we have, I think there is one that has the Large Matter Cloud in it. But we have hundreds. We have hundreds.
And did you check one of the reasons why the constraint simulations are interesting was to try to solve small scale problems that one simulations are not able? Did you make any progress, for example, in playing with satellites or something like that?
There is a paper where we mimic, but not in the Hestia yet, where we mimic in the old CLUE simulations exactly the observational techniques that were used for the Panda survey, and we found the plane. Like using the same type of selection and the obscuration because of the galactic plane and all of that, we actually found the plane of satellite galaxies, but in this one particular simulation. We haven't returned, I don't know why we haven't returned in the latest simulations to look for the plane. I talked to Noam about that because one of the motivations to continue was, can we still find it when we use this new code, better resolution, better subgrid modeling? Is it reproducible? Was it just a chance encounter in this one simulation, or can we reproduce it with a different code, different subgrid physics, all more modern? We haven't looked at it. I can understand your frustration now because it should be the first thing to look at. I can't tell you why.
We need another student.
Yeah. I mean, we are a large collaboration, but we are not as large as other collaborations in computational cosmology. And we don't have access to that many funds as other collaborations.
So, but do you think it's part of the reason we see them on the plane is because of the selection effect? So,
To be honest, I don't. To be honest, I don't think so. I don't think so. I think we were lucky there. To be honest, I think we were lucky to find them.
You find it applied. You say that you apply the same.
Yeah, but that was
there is a bias, but in 3D there was a plane.
Yeah, there was a plane, but I actually think that we were lucky. And can we stop the recording here? And I actually think that we were biased because we wanted to find something. This is what I told you before of the Council of Giants. I started looking, having the Milky Way at the center because this is what McCall found. But this is biased. I think we were hoping to find something. And if you look hard enough, you might find. I don't want to discredit the paper. I have an offer on the paper. We were happy that we found it, but I think
it's okay. I mean,
yeah.
Then it's not a problem for the tomorrow. You got by chance. You have to see how
the place of surface can also be transient.
Yeah. Exactly.
I mean, you say that you need the velocities of the galaxies to test if those are the galaxies in the filament, but you have the maps of the flow. The map that you use for the initial conditions is made with the velocities with all the so you have the velocities there, right?
This is right. This is another survey. This is not the LVG survey. That's the cosmic flow survey that has positions and radial velocities. Sure, we also looked in that survey for the council, but we couldn't find the council in there. And then we talked to the creators of that survey saying, you should only use the velocities.
Well, then you can just say combine the velocities of that survey with the velocities.
Yes, that's another Trabajo in the master. To make the cross-correlation between these two catalogs. Yes, that we could have done. Yes, I agree, we could have done that.
And I'm not surprised that you don't find the
one more thing in that regards. I don't know the exact details of this cosmic flow survey, but they are also doing a grouping. We are interested in the large-scale flows and not in the exact velocity of this one galaxy at that point. So they start to smooth the field in a very fancy way using filters and whatever, and I don't have a clue about that. So in the end, it is not as easy as taking this velocity of the galaxy, find it in that catalog, and then assign it to that. It's more involved than that.
Okay. Well, just that they're asking. I mean, when you saw the Plopotectus simulation, I mean, it was very similar to the local. You didn't compare it directly because you don't have any relations with the partner, but it looks like very similar. And in fact, you use these flows to the initial conditions. I'm sure that the galaxies were also there in a filament. So I'm surprised that you don't find the Council of Giants because. I mean, it looks also like the Milky Way or the Local Group is also surrounded by filament.
Look, we looked in the Cosmic Flow survey, we looked in the LVG survey, and we looked also in McCall's table. Yes, we had these three data to find the council. And Cosmic Flows, I can't remember, at some point we couldn't find it, and then I talked to Jenny Sauce, who was very involved in the survey, and she told me, don't use it for these 3D point searches that you are doing, because we are doing 3D point search. So we did the conversion of all the data into a 3D supergalactic plane coordinate system, and she said, don't do that, don't do it. And then that's when we said, okay, easier for us, we just dropped it.
I'm not saying that. I'm saying that I'm surprised that you don't find it in the simulation because you have the same structure like. Also, like you have the filaments surrounding the local group, and it looks like you should find it if it was just
because it's probably just a transient structure. So if you have your galaxies flowing like this, and your galaxies flowing like that towards Virgo here, and now you happen to have in the simulation. In the real data you have this situation, you find it. But in the simulation, you have this situation and then you don't find it. And it will also not be there a few snapshots back, because it's just a random snapshot.
Yes.
Mhm. That is my suspicion of what it is.
Thank you. Sorry.
Did you check if the Milky Way plane is perpendicular to this?
It was, yes. In that, but this was not the Hestia, those were the old CLUES simulations. Like the Gadget 2 Springel-Hörnquist model simulation, where we found this plane perpendicular to the disk of the Milky Way. That's a paper from 2015, if I remember correctly.
You mentioned Auriga for your upgrade of CLUES. I would like to know exactly what are you using from Auriga? Is the approach, is it the zooming, is it the physics?
No, it's the physics, it's a subgrid model. It's exactly the same subgrid modeling. So the gas cooling, star formation, the feedback scheme is identical to Auriga. In the latest CLUES simulations that we now call Hestia. The old CLUES simulations didn't have a name, they were, I don't know. But now there is this Hestia, and with Arepo and the Auriga model. But look, you mentioned this, Zoom. These are all Zoom simulations.
Okay.
Everything that we are doing here is Zoom simulation. We are zooming in onto the local group actually, onto the Milky Way and the Andromeda.
I'm interested that you match, or you constrain your simulations with the cosmic flow, but then you use the WMAP or CMB cosmology constraints for the Hubble constant.
Yes.
Is there some, is there some problem with consistency of using a 67 kilometers per second per
Yes, because if I understand, there was at every CLUES meeting there is a discussion about the value of H0 when it comes to the normalization of the velocities. Yes, you need to make an assumption about H0 when you, because you have radial velocities and they are influenced by the Hubble field. So you need to account and correct for that. So you need to make an assumption about H0. Yes, and then if you use in your simulation another H0 value, you might screw things up.
Would you use something closer to 73 to match the local structure?
I think it's 71 that we are using for the simulations, and also for the normalization of cosmic flows. But I would need to look it up, but I think it's 71.
Any other questions?
Maybe a stupid question, but it's more or less related to what you were saying, was asking but in a different way. And you try to put, like, knowing the underdensity of the local group, to put that into the instance ladder to see how that will impact to the different distance estimates as you move away.
No.
Because you are already a formula person. Many of the CFA distance will be affected by that. So it will also affect to estimates.
No, we
Yes,
have one.
Other question online? Any question online? No?
Well, have you run the simulations in the future to see if the Milky Way and Andromeda merge?
There is one simulation, yes. Okay, this is not my computer. If I had my computer connected now, I could show you in 10 seconds exactly that simulation. Not for the Hestia, not for all the 100 simulations that we ran, but just out of fun. For one simulation, at the start of the collaboration, we just had exactly the same thing. What happens to Milky Way and Andromeda? Do they crush into Virgo, or do they merge first? In that particular setup, they merge first. But I don't know what happens if we now take the latest simulations. This is okay. No. Hang on. How do I go back to that screen?
Go to the PowerPoint icon on the back. There you go.
What is it?
Because there is one part that actually shows a picture of what I said earlier. This flow in two distinct filaments towards Virgo. Okay, anyway, I draw it here. I draw it here. Don't worry.
There you go.
And can you jump to prefer? Oh,
sorry.
Where is the mouse?
Yes.
Okay, and I want to jump because there is a nice picture in there. If I remember correctly. Okay, this is not working anymore. Yeah, this was even before we did the same panda selection and blah blah blah, where we also used as the motivation the planes of satellites, and this is the picture that I wanted to show. And in the end, the follow-up paper to this was using the panda survey selection criteria to our satellite, because this paper gave the hint that yes, the plane is really there, and the origin is. Here is a tiny filament, here is a tiny filament towards Virgo. So this is the velocity vector of M31 at Milky Way. There we go to Virgo. I can't remember anymore what these two vectors are. So they are flying here, and while they are flying, they scoop up the galaxies in this direction. So there is the paper is called preferential infall into the local group. So this is why they now then also start to orbit like that. And let me see. Yeah, this, where do I find? Okay, this is all the quantification of it. Yes, we do find preferential infall. These are the poles of the galaxies that start to. These are the entry points of the galaxies that start to orbit. It is not looking for the plane yet, but we found that all the galaxies in the Milky Way and in the Andromeda fall in from preferred directions, from here, not from here. And then they probably start to orbit, and that was the next paper done by another PhD student, where he said, okay, now let me look for the plane, doing the same blah 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 selection, and we found it. And the explanation is basically this. So the explanation in the end is you require the local cosmography. Otherwise, you are unable to generate the plane. You need this scooping up in a certain direction.
Other question?
Regarding the star formation and depends on satellites, in some recent surveys or Milky Way analogs, it looks like the local group is special, and we are pointing in a high grade satellites. Did you find some trend that if you put Andromeda and Milky Way analog and the Milky Way, you are pointing more satellites than?
Where is that paper? It's
Yeah,
here.
star formation.
Yeah, star formation. Actually, we find the opposite. We find that in our simulation, I mean, this is not, yeah, it's our theoretical model, we find that galaxies enter and actually can continue forming stars as satellites. So this is the opposite of quenching, I guess.
Well, they continue is not good. The question depends. Are they still forming at a lower rate or higher?
I need to look at the plot. This is, hang on, how can I? Star formation in galaxies. So, okay, no, this is not, I don't know why this stopped working. Ongoing star formation, and these are the star formation rates. And basically, okay, what do you see here? Time since the Big Bang or look back time, I can't remember. The red line here is the entry time into the Milky Way. And then for some of them, you still have star formation going on afterwards. Not for all of them, but for some of them you have star formation. And now I think your question was, whether this peak is as high as the early star formation.
No, but it's true that it doesn't. I mean, for some of them, yes, but for many of them, it doesn't. It's not quite. I mean, it continues with the same slope, the star formation history,
for instance, the peak was approaching and it started forming stars like crazy. And I mean, now we try to understand why did this thing not form stars and why did this thing form stars like crazy. But I think the explanation is obvious. It's not quenching, it's gas suppression due to RAM pressure, and it requires close pericentric orbits and things like that are required for that to happen. But what you were asking, I think, was exactly
like comparing the concept.
No. You wanted that. Oh, this thing now enters. Boom! It goes to zero.
Not really. I was thinking of comparing the concept fraction against the stellar mass. And for the low mass halos and the low mass satellites, the quenching is really efficient. But for the high mass satellites, as they have more storing pressure, they can keep the gas. And in the local group, we are quenching even except the Magellanic Cloud, we are quenching on the satellites. And that's a bit weird if we compare with another Milky Way analogs. So maybe comparing with.
Okay, this is. I don't have a slide for that, but thanks for the comment.
Okay.
Mental note taken.
Any other question? Online, are there any questions? Well, if not, let's thank Alexander
We're not going back because you know
Thank you all for joining us. Thank you very much.